Yeah. Okay. Good morning, everyone. Thank you so much for coming to the fourth instantiation of PPML at Crypto. So today we had a hard time because of WAC happening at the same time, but thank you so much for attending. We're going to start the session today with the second talk, not with the first one. And this is going to be MicroFedML, privacy preserving federated learning for small weights. Guo is going to give the talk, and this is joint work with Antigone Policrinado, Elin Shi, David Bird, and Tucker Balch. Thank you.
Yeah, thank you very much for introduction. So my name is Xue, and I'm from JP Morgan AI Research. And today I want to talk about our work on secret aggregation for small domain. This is a joint work with Antigone, Elaine, Tucker, and David. So in this talk, I want to first introduce what secret aggregation problem is and why it is needed in several practical applications, including privacy preserving federated learning. And I will quickly review several existing works and talk about our technique. And at the end, I will include the simulation results and the comparison between our protocol and previous works. It does not work. I guess the keyboard is not working. Okay. Oh, yes. Thank you. Yeah. So, so secret aggregation refers to a problem in which a set of users and one or a few central servers want to collaboratively calculate the aggregation result of secret input of the user. So basically, each user has a secret input in every iteration, and they want to calculate the sum of their secret input with the help of the central server. But they don't want any other party, including the server and also other users, to know their own individual input. So there are several applications of this primitive, including voting in both applications, and also counting the number of page accesses in internet browsers, and also collecting the positive results of COVID-19 exposure in the notification system. And also, it can be used in privacy preserving federated learning to aggregate the local update from the users. Remember that in federated learning, every user needs to send its local update to the server so that the server can update the global model with the aggregation of the local updates, and the user don't need to send their private training data. However, several existing works also show that this is not enough to protect the privacy of the training data, because the local update can still leak sensitive information about the training set. So here we need secret aggregation to let the server only learn the aggregated update from the users rather than individual updates of every participant. And because we focus on small input domain in this work, our work will be suitable for federated learning with gradient specification or quantized neural network or weight regularization. And now I'm going to introduce the problem setting we focus on. So we consider the following model. Here, we run the protocol with one single central server and n user as participants. And the users, they will only talk to the server, and they do not talk to each other. And users might drop offline and come back online later. And we also assume that the server and less than one half in some honest case, or less than 1/3 in malicious case of users can be compromised. There are several existing works investigated this problem, and the popular ones includes this paper published in 2017 by Google, which achieves communication cost of order n per iteration per user. And they also have a follow-up work published in 2020, which improved the communication cost to autolog n with user grouping technique. But this work also increased the round complexity of each iteration, and it slightly changed the security definition, because now it relies on the probabilistic user grouping. There are several other works also tackle this problem, but they either only consider the semi-honest case or they do not allow offline users to come back online later. So in this work, we focus on comparing to and improving the first two works, and our results achieve the same level of security definition, and we reduce the round complexity of each iteration. We also improve the practical communication and computation efficiency by 50 to 100 times if the input domain is small. So here is a quick comparison of the asymptotic communication cost per user per iteration. Here, the red underlying text is only needed in malicious case, and the black text are needed in both semi-honest and malicious case. Here, the left two columns are from the previous two works, and the right two columns are our work. You can see that our work, in every iteration, we require less number of rounds, and also in every round, we achieve nearly constant communication cost, while the previous works in every round, each user needs to send and receive order n or order log n elements in every round. So now I want to talk about our technique. To start with, I want to quickly recap the primitive of T-elephant Shamir secret sharing. Remember that this primitive allows the secret holder to divide the secret into n shares such that NT of them can be reconstructed into the original secret, while any less than T of them does not leak any information of the secret. And this scheme also has a additive homomorphism property, which means if we have two secret holders and each of them use T out of n secret sharing to share the secrets with the same set of users, then if each user adds the shares they receive up, this will give us the share of the sum of the secrets. So basically, the sum of the shares is just the shares of the sum. And this immediately gives us the naive solution to the secret aggregation problem we mentioned earlier. We can just let everyone secret share its secret input. To be more specific, let's consider the following solution. Every user with their secret input now first secret share their input among all of the users, and they encrypt the shares with the symmetric key they agreed with the other users in advance, and sends the encrypted share to the server, and server forwards the encrypted share to the corresponding receivers, and every user now decrypts the share with the symmetric key and sends the sum of share to the server. Because we have additive homomorphism, the server can now reconstruct the sum of the secret from the sum of shares. And this solution already tolerates user drop offline because we have threshold T. As long as there are at least T users be online and sending the server the sum of shares, the server can always reconstruct the sum of the secret inputs. But this solution also requires order n communication per user per iteration, because even when every user only have one fresh input in every iteration, it still needs to secret share it among all of the users, which requires sending and receiving order n shares. So the natural question here is, can we share something just once and reuse it to hide the fresh secret input in every iteration to reduce the communication cost? And the solution we propose is to add a layer of reusable random mask. So to be more specific, we add a one-time setup phase before all of the aggregation happens. So in this setup phase, every user uniformly randomly pick a random mask R and secret share it in the same way as described before. So at the end of setup phase, every user should have one share of the random mask of each other user. And when aggregation happens, every user will have a secret input. And in the first step, every user sends the masked input, which is the sum of secret and the mask to server. And the server sends back the online set. And every user now sends the sum of shares from the online set to server. And because we have additive homomorphism, the server can now reconstruct the sum of the random mask of the online set and remove it from the sum of secret masked input. But you might have already noticed that this hasn't given us reusability yet, because if we consider next iteration, if someone drops offline and everyone still uses the same random mask, then in the first step, every user still sends the mask input and the server sends back the online set, and every user sends back the sum of shares of the online set. Now the server can get the sum of the masks of the online set, but this not only lets the server calculate the sum of the secret of online set, but also it leaks the mask of the offline user. So now immediately the offline user's historical input will be leaked. Sorry. So in this solution, we cannot reuse the mask yet. We still need to secret share a fresh mask in every iteration, but this is already a simpler version than the previous work published in 2017. Because the previous work requires each user to share 2 masks, and the server needs to do reconstruction for every user. But here we only need to secret share 1 mask, and the server only need to do 1 reconstruction for all of the users to calculate the sum of the masks. But here we still want to make these random masks reusable, so that we don't need to secret share a fresh mask in every iteration. To achieve this goal, we need to further hide the sum of the random masks. To hide this mask, we need an additional assumption, which is DDH assumption in our proof. But here, I'm just going to high-levelly introduce it. So the intuition is that the discrete log in a large enough cyclic group is very hard if the exponent is uniformly randomly chosen. So remember that this assumption only holds when this R is uniformly randomly chosen. If this exponent is from a small, relatively small domain, then both the exponentiation and the discrete log will be easy. There are several existing works it has the technique to calculate discrete log in small range. So with this assumption, we can now further hide this mask in the exponent of the generator of the group. So we modify our previous protocol to this version. So the setup phase is exactly the same. Every user still choose a random mask and secret share it. But in the aggregation phase, in the first step, every user now, instead of sending the masked input directly to the server, now it sends it in exponent. And next step, server still sends back the online set. And every user also sends the sum of shares in the exponent instead of sending it directly. And because the reconstruction of Shamir secret sharing only involves linear operations, this reconstruction can happen in the exponent. So the server can reconstruct the sum of R mask in the exponent, but because R is uniformly randomly chosen, the server cannot do the discrete log to extract the sum of the masks. Now it can remove the sum of masks from the G to the sum of mask input, and it will get sum of secret in the exponent. And because we assume that the secret inputs are from a relatively small domain, the server can now calculate discrete log to get the sum of secret. This is actually the first solution we give. And here is the description of our protocol. I'm going to skip the details and notations here, but you can see that setup phase requires 3 rounds, and aggregation phase requires 2 or 3 rounds, depends on the adversarial setting. And in the first and last round, every user only needs to send one single group element to the server in every iteration. But here, you might have already noticed that the server still needs to let every user know who are online and who are offline in every iteration. And this information needs to be represented in order n bits. So to further reduce the asymptotic communication cost, we improve this version by user grouping technique. I'm also going to skip the details of these parts now. But the basic idea is to divide the whole set of users into small groups of size order log n, which reduce the communication cost also to order log n per user per iteration. And we also achieve lower round complexity than the group version of the previous work. We implement our protocol and also the previous work with ABAS framework, which is a discrete event simulation framework, and run the simulation on AWS machine. And here are some comparison of the running results. So here is the comparison of bandwidth cost per iteration. Here, the y-axis is the size of the message sent by each user or by server in bytes. And the x-axis is the number of total users. And here, we assume that the aggregated results can be represented in 20 bits. And for the 2 group versions of previous work and our work, we use group size 100. And here, the brown and black line are the previous works, and blue and red lines are from our work. It looks like it's close to 0, but actually, it is above the 0 line. But because of the scale, it does not show very clearly here. And here, we assume that the aggregated results can be represented in 20 bits, but with higher length or larger range, we still have like techniques like rainbow table or kangaroo algorithms that can also handle larger input. And this slide shows the comparison of the computation time per iteration for each user or for the server. Now that y-axis is the computation time in seconds, and other settings are all the same. And here, the red and black lines are for the previous works, and blue and brown lines are our work. In conclusion, in this work, we propose a secret aggregation protocol for small input domain, and in our work, we only need to secret share one mask once in setup phase, and we can reuse it in every iteration. And with this reusable mask, we achieve lower round complexity in aggregation phase, and we also achieve better practical performance when the input domain is small. So this is all I want to talk today. Thank you very much.
Thank you. Thank you, Julia, for your talk. So we have a minute or two for questions. We want to ask the audience, also the ones in Zoom can ask in the chat. And if the audience wants to ask a question, we will kindly ask you either come here or you can ask there and we ask the speaker to repeat the question, please. It's up to you.
Sorry, I didn't hear the first part clearly. Would you mind repeating? Sure. Oh.
Hold on, let me give you the microphone. I think it's hard to listen for that.
Do you mean here?
Yeah. So my question is, like, you're able to calculate the district log for the sum of the secret share. Why can't like the malicious server calculate the district log for the sum of the reusable mask?
Oh, that is because the reusable mask is uniform randomly picked from a very large domain.
Oh, it's like our domains are different
Yeah,
for both.
this is
Oh,
why
okay.
we focus on the small input domain, so that the sum of the secrets is much smaller than the masks.
Okay, like I thought both of them are sharing the domain. Thank you.
Thank you.
Thank you. Is there any other question? Please.
Hi, so about this reusable mask, if the same mask is used by the same client over iterations, then wouldn't the server be able to compute the division and then
Oh, yes.
find the difference?
Yeah, sorry, I skipped this detail here. So remember that we need a generator to be the base of the exponentiation. In every iteration, we use a random oracle or hash function that take the iteration number as an input. So in every iteration, the base will be different. And with DDH assumption, it guarantees that the server cannot extract effective information about the random mask.
Thank you.
Thank you.
Okay, with that, all the questions, let's take them offline. Let's thank the speaker again.